This video, I'm going to introduce the first principal component. And this is based on projections, which we cover in linear algebra, Math 330. My assumption, based on course prereqs, is not that you have taken that. So um, it's all fine because Python is going to handle the underlying math anyway. So we don't need to know the formula for a projection, but we do need to know what a projection is. And I say projection. I really should be saying orthogonal projection. So orthogonal means at a right angle, a right angle projection. And the idea is this. Suppose you have a line, maybe. Watch me try to draw a straight line with the trackpad. Well, it could be worse. And you have a point that is not on the line. Well, you can project the point orthogonally onto the line. You can create a right angle like so. And now this point here is the projection. Okay, I promise I won't try to write full words again. This is pretty painful. And the same idea if you have, instead of a point and a line, if you have a point and a plane, and now we're really coming to the limits of my artistic ability. But suppose you have three-dimensional space. And this vector, this axis, and this axis, I mean, together they define a plane. And you have some point that is not on the plane. Well, you can project it down so that it is onto the plane, and so on. But this is the really important one for our purposes, projecting onto a line. So suppose you have some data. You have a point there and a point there. And this is maybe the point, I don't know, 2, 7 and 3, 8. So your data is two-dimensional. Suppose you wanted to go from 2 dimensions to 1 dimension. You could do that in the following way. Draw a straight line and then project these points orthogonally down on to the straight line. So now from 2, 7 and 3, 8, if this is the x-axis, You've replaced that first point with 2, and you've replaced that second point with 3. So we've gone from 2 dimensions to 1 dimension. And of course, the price of this is that we have lost information. Now, I drew this line and I did this projection, but I could have drawn another line and projected onto it. And something we notice is that if we have these 2 points, for example, and we project them onto this line, these projections are close together. I know I promised, but here we are. Those points are close together. Whereas if instead, and let me put where they are, right? The first projection was there, the second projection was about there. If, on the other hand, we drew this line and we projected onto it, these projections are far apart. So some projections will cause your data to be more clustered together. Other projections will cause your data to be spread further apart. And I am claiming that for most of our purposes, we want data to be spread out. We want our data to be as varied as possible. Why is that? Let's state a goal we might have. Take some data points and sort them into groups. And we have the points 1, negative 15, 1, negative 32, 1, 47, 1, 95, 1, negative 49, negative 149, go with it, and 1, 5472. Well, I'm not saying there's only one way we could do this, but if I gave this data to someone and said, I want you to put this into 2 groups, I think most people would probably end up with this, right? We can sort the data based on whether the second component is negative or positive. We can't sort the data based on the first component because the first component is always the same. If we tried to sort it based on the first component, all of the data would have to go in the same group. So the reason we're able to do something like this is that the y coordinate varies. And therefore, we want our data to vary. Our data varying is the only way we can do something like this. And this brings us to the idea of principal component analysis. So don't read it. I mean, you can read it if you want to, but let me try to get at what this is saying. So suppose we're looking once again at a document vector. Every different word in the book gives you a dimension. So you're in a super high dimensional space, or in at least, for day-to-day purposes, 15,000 dimensions seems like a lot. You're in a high dimensional space, and we're going to reduce this to one dimension. How are we going to do that? Well, you can draw lines in 15,000 dimensional space. It's of course impossible to visualize, but that's linear algebra fact, I guess I might say. So if we have a line in 15,000 dimensional space, we can project onto the line. And we know that we want a lot of variance. We know that variance is good. So we're going to find a line through the data such that once you project onto that line, the data is as spread out as possible. And this line is called the first principal component. So we can have a second principal component and a third principal component. But we take our 15,000 dimensional space, and to start with, we project it onto a line. We make it one dimensional. And that would be a pretty major reduction in dimension, right? So this is a reasonable question to ask. Can this one-dimensional summary of 15,000 dimensional data possibly be good for anything? And in the next video, we will look at the document vectors of some real books, and we'll see what happens when we do this analysis.